Hello everyone. Today we are going to look at the implementation of deep neural networks using the scikit-learn library of Python. And specifically in this video, we are going to see the implementation of deep neural networks for solving regression problems. So there are different types of neural networks. So here our concentration will be on that of what we call multi-layer perceptron. And here the aim is to find a certain target function f that maps a p-dimensional input space X to a q-dimensional output space. So this mapping may represent either regression or classification problem. So there could be p inputs in the input space. So here p represents the number of input dimensions. And regarding the output space, there could be q outputs. So q represents the number of output dimensions. So in the usual univariate regression models or classification models, the number of output dimensions are usually assumed to be 1. So here Q represents 1 for that of the usual regression problem or classification problem. So like that of any supervised learning algorithms, the aim is to create a mapping from the input space to an output space. Therefore, unlike that of the linear models, here in the case of deep neural network, there will be one or more nonlinear layers, which are called hidden layers, between the input layer and the output layer. So the aim is to create a mapping from X, which is the input space, to Y, which is the output space. So if one or more hidden layers are added inside this input and output space, we call the method as a deep neural network. So for a set of input features, let's say X, and a single target feature Y, the multi-layer perceptron representation could be something like this. So if we have, let's say, three inputs, X1, X2, X3, and if we have a single output, then here we have just what we call one node. This circle represents a node. So in the general representation, the mapping could be from a p-dimensional input space to a q-dimensional output space. But here we are particularly concentrating on a single output space. The mapping is, let's say here, from a three-dimensional input space to a one-dimensional output space. So in the usual standard regression or classification models, here we have these inputs and here we have these outputs. We don't have this part. Then the mapping is just from X1, X2, X3 to that of this output node. But now in between these inputs and these outputs, we have added another part here which is called layer. And particularly this layer is called hidden layer because it is found in between the inputs and the outputs. So here we have the layer consisting of the inputs is called input layer, and the layer consisting of the outputs is called output layer, and anything in between that it is called a hidden layer. So here we have input space. Here we have just one node for X1, another node for X2, and another node for X3. So these three nodes will have a connection with each node of the hidden layer. So X1 is connected with this node, and this node. So specifically here, the hidden layer has three nodes. So each of the inputs has a connection with each of the nodes in the hidden layer. Similarly, each of the node in the hidden layer has a connection with each of the node in the output layer. Here particularly, the output layer has only one node. So we call this as a multi-layer perceptron. A multi-layer perceptron. So the left most layer, this layer is called the input layer because it consists of that of the inputs, and that's of the rightmost layer. This layer is called an output layer. Particularly here, this output layer consists of one node, like that of the usual regression and classification problems. In the case of having what we call multi-class classification, for example, like that of multinomial logistic regression or ordinal logistic regression, the number of output nodes will be more than one. So those layers that are in between these input and output layers are called hidden layers. So any layer in between this, it is called a hidden layer, or in general there could be one or more hidden layers. Therefore, everything inside the input and the output layers is called a hidden layer. So each neuron in the hidden layer will make a certain transformation by taking values from the previous layer, and the transformation will be something like a weighted linear combination. So for example, this node is nothing but x1 times the weight corresponding to this node plus x2 times the weight corresponding to again this node plus x3 times the weight corresponding to this node. Or for clarity, just let me go to the scikit-learn documentation. So here we have input nodes, which represents that of the input layer, and here we have an output layer. No, that's the hidden layer, and here we have an output layer. So in the input layer, we have x1, x2, x3, and so on. It consists of all the inputs. Plus, we have what we call a bias term or an intercept with certain constant inputs, let's say 1. Similarly, in the hidden layer, we could have just hidden node 1, hidden node 2, and so on. And again, this hidden layer has also a bias term or intercept term, whose input is again 1. So here, for example, A1 is nothing but here plus 1 times the weight corresponding to this arrow plus x1 times the weight corresponding to this arrow plus x2 times the weight corresponding to this arrow plus x3 times the weight corresponding to this arrow, and so on. Similarly, A2 is nothing but plus 1 times the weight corresponding to this one or this arrow plus x1 times the weight corresponding to this arrow plus x2 times the weight corresponding to this arrow, and so on. Similarly, the final output y or f of x is nothing but 1 times the weight corresponding to this arrow plus a1 times the weight corresponding to this arrow plus a2 times the weight corresponding to this arrow, and so on. Therefore, each of the node in the hidden layer transforms the values from the previous layer with a weighted linear combination of the form w nodes plus w1 x1 plus w2 x2 plus wp xp. Now here w node is nothing but here we have one node here representing a constant, even if it is not shown here. Here we have one node. That node has an input of 1, then x1, x2, x3. Similarly, in the hidden layer, we have these 3 nodes, plus again we have another node here. So this node represents a value of 1. So the linear sum or the linear combination is going to be followed by a certain nonlinear activation function, which is, let's say, called phi of let's say h, that maps a certain real number to another real number. It could be a logistic or what we call sigmoid activation function, tan h, which is called hyperbolic tangent, or ReLU or rectified linear unit. So in each node there is a certain linear transformation. Here there is a certain constant, not constant, that's just here we have a single value. This single value is going to be transformed into another single value. So the mapping is just from a single dimensional real number to another single dimensional real number. So when you say multi-layer perceptron, it is a specific type of what we call feed-forward neural network. So feed-forward means there is no cycles, information flows forward only, or from the input space to the output space. There are other types of neural networks which receive feedback, but when you say multi-layer perceptron, just the information flows from the input space to the output space. So it is one directional, or information flows in a forward way only. And the other, in the multi-layer perceptron, each layer is fully connected, or what we call dense. Here we have x1, it is fully connected with all the nodes of the hidden layer. x2, it is connected with all the nodes of the hidden layer, and x3 is connected with all the nodes of the hidden layer. Similarly, each node of the hidden layer has a connection with the corresponding hidden layer or output layer nodes. So we call this dense. There is no discontinuity. For example, x1 is connected with these three nodes. But if we terminate, let's say, this arrow, in that case, x1 is not fully connected. Similarly, if we consider x2, x2 has a connection with these three nodes. But if we terminate this arrow, now the connection of x2 is not fully connected. It connects with the second and the third nodes, but it doesn't have a connection with the first node. So when you say fully connected or dense, just each node has a connection with their corresponding subsequent nodes. And actually there is no strict magic number for determining the number of hidden neurons. For example, here we have three hidden nodes, or let's say neurons, but the number of nodes are going to be determined somewhat using what we call a subjective way of determination. And in particular, in scikit-learn, the default number of hidden nodes is assumed to be 100. If we include one hidden layer, by default, the number of nodes in this hidden layer is assumed to be 100. So here, in general, here you have input layer, hidden layer, output layer. This network is called single hidden layer neural network. Single hidden layer neural network, or we call it as a two-layer neural network. The input layer is not actually counted as a layer in calling the network, because this input layer only feeds the information as it is. No transformation is going to be applied. Therefore, this layer is not actually counted as a layer. Here we have one layer, here we have another layer. Therefore, we call this as a two-layer neural network. Two-layer neural network, or we can call it as a single hidden layer neural network. So in terms of the hidden layers, this is a single layer neural network, but in terms of general layers, this model is a two-layer neural network. A two-layer neural network. So in determining that of the number of hidden neurons or hidden nodes in the hidden layers, there are some starting points that can be considered as rules of thumb, but there is no hard and fast rule to determine how many nodes should be there in the hidden layers. So usually a power of size 2 is going to be considered, like that of 8 nodes, 16 nodes, 32 nodes, 64 nodes, and so on, because these values are assumed to fill well in memory blocks and they scale naturally. So it is usual and common in the neural network implementation to consider number of nodes in each hidden layer as 8, 16, 32, 64, 128, and so on. And the other, if there are two or more hidden layers, here we have a single hidden layer, but if we have hidden layer 1 here, another hidden layer here, another hidden layer, something like that, we have what we call a pyramid shape way of determining the number of hidden nodes. So in the pyramid shape, the first hidden layer will have a larger number of nodes, let's say 64. Then the second hidden layer will have somewhat a smaller number of hidden nodes, let's say 32. And the third one will have something like smaller than 32, let's say 16. So this way of determination is called a pyramid shape way of determining the number of nodes in the hidden layers. And another way as a starting point is also to consider what we call input-output average rule. So the number of hidden nodes can be determined as number of input nodes plus number of output nodes divided by 2. But in general, there is no just strict or hard and fast rule to determine the number of hidden nodes of the hidden layers. So in general concept, if the number of neurons are too small or too few, the model may underfit. So if the model is underfitting, that means the model cannot capture the complexity or the underlying patterns in the data. On the other hand, if the number of nodes are too many, in that case, the model may be what we call overfitting. That means instead of learning the patterns of the data, the model may try to memorize the training set in general. So memorizing is quite different from that of learning. Our objective in machine learning is to learn or to understand the patterns that are hidden in the existing data. But memorization is remembering the data without learning the patterns that are inherent in the dataset. So if there are too many neurons or too many nodes, in that case the model may have an overfitting problem. So let's consider a multi-layer perceptron for regression problems. And first, let's upgrade that of the scikit-learn library to the latest version using pip install --upgrade scikit-learn, let's say -q. This -q is not to display certain outputs, just to upgrade the scikit-learn library in a certain silent or quiet way. So here we are going to consider the data sets that we have considered in the previous tutorials. That's of the Boston housing data set, which we have variables related to crime rates, proportion of residential land, and so on. Finally, our outcome variable for the regression model is that of the median price of the homes. So now we have upgraded our scikit-learn library. So let's also import these pandas and numpy libraries, which are frequently used in any analysis. So these pandas and numpy libraries are imported. Now let's import the data that we are going to use for implementing these deep neural network concepts for regression problems. So this is the data that we are going to implement deep neural networks. Here we have price, which is our outcome variable of interest, and all the other variables will be considered as covariates or input features. So there are 506 rows and 14 columns. So that means there are 506 observations and 14 variables. But of these 14 variables, one of them is our outcome variable of interest. So that means there could be certain input features or covariates. We can also call the method info over our data frame. So this displays that of the some descriptions related to the variables, including number of non-missing observations, as the data type of each variable, and so on. And we can describe each variable using the describe method. So this describe method displays some summary statistics, including the count of the observations, the mean, standard deviation, the minimum, the first quartile value, the second quartile value, which is the median, the third quartile value, and that's of the maximum value for each numeric variable. So once we import our data, the first thing that we are going to do is we need to split the data input features data frame and output features data frame. So first to get that of the input features data, we need to remove that of the price column because price is our target variable of interest. So from the housing data frame, drop this price column. So this is our data frame consisting of that of all the input features. So this input features data has 506 observations and 13 covariates. And for that of the outcome feature data, we have to extract the price variable alone. So here we have a single output feature price, and this has 506 observations. And next we have to identify the quantitative and categorical covariates in the that's of the covariates data frame, because we are going to apply different types of transformations for the quantitative and categorical covariates. So it is necessary to identify those quantitative and categorical covariates. So of these variables here, we have this variable which is chas or a dummy variable indicating whether the house is near to that of the Charles River or not. So the only quantitative variable here we have is this chas variable. All the other variables are quantitative. So this chas variable is our categorical variable. We have a single categorical variable, and all the other variables are quantitative variables, so we can consider all the other variables as quantitative features. So here we have this number of quantitative features, specifically the number of features which are quantitative is 12. So we have one categorical input feature and there are 12 quantitative input features. Then next we need to split the data that's of into train and test sets. Both the input features data and the target features data should be split into train and test sets. So for this purpose we need to import that of the train test split function from a scalar model selection, and then we need to supply just in the train test split, we need to supply the input features data frame and output features data frame, and we have to present that of the test size. So here for example we specified as 0.2, so 20% of the observations will go for testing and the remaining 80% will go for training. And for ease of reproducibility, we can state the random state to a certain number. So here now the train test split is done. So our data frame of the test set consists of 102 observations, and the train set consists of 404 observations. So a splitting is done into train and test sets. Then once we split the data into train and test sets, next we have to transform the input features. Those qualitative variables should be numerically coded if they are not yet, and those quantitative variables should be either standardized or normalized. So for encoding the categorical variables, we are going to consider what we call one-hot encoding, and for the quantity variables, we need to consider either standardized or the soft-minimax scalar. So to transform both of them all in one, we can consider what we call this column transformer function. So for example, for the qualitative variables, we need to call this one-hot encoder. And we can say drop first or last to consider the first as a reference category or the last as a reference category. So this is the instantiation for making a one-hot encoding for those qualitative or categorical variables. So here drop first, so the first category will be considered as a reference category. In fact, for our dataset, for example, even if this just variable is a qualitative variable, this is already numerically coded, specifically using the soft dummy coding 0 and 1. So there is no need of recording this variable. So, but just to see how the categorical variables are encoded, we can implement this one-hot encoder transformation. There is no hurt that is going to occur. So, and for out of the quantitative covariates, we need to consider, let's say, minimax scalar. We can also consider that soft standard scalar. Usually, if we assume the quantitative variables to have a certain, let's say what we call a normal distribution, in that case, standardization is recommended to be applied. But if I assume the input features have a different distribution, we can use that soft minimax scalar. But in general, again, whether to use minimax scalar or standard scalar, there is no hard and fast rule. Just we can try each transformation and then we can select the one that works best for us. So for that of the quantitative variables transformation, we can use this minimax scalar. So it says feature range 0. So if I go to the documentation of the scikit-learn, so the feature range is going to be restricted in between 0 and 1. If we are interested, we can change, but by default, each quantity feature is going to be converted into a value between 0 and 1. So these are instantiations. No transformation is done yet. If we point to here, it says not fitted. Here, not fitted. So we created an instantiation for transforming the quantity features and thus of the categorical features, but the transformation is not done yet. So to make a transformation both in one for those qualitative variables and quantitative variables, we can use this column transformer. So column transformer, we can label this as categorical encoder. The cat transform is this one-hot encoder, drop first, categorical features. Here we have only this just variable. In fact, this variable is already coded using value 0 and 1, so there is nothing that makes different by using this one-hot encoder. And for quantitative scalar, we can name this whatever we want to term quantitative scalar, the quantitative transform, this minimax scalar, and then we can call those quantity features, which are these 12 quantitative input features. So let's instantiate. Again, this is an instantiation of categorical encoder is going to be applied for the class variable, and the quantitative scalars is going to be the quantitative scalar is going to be applied on these features, specifically which is the minimax scalar. Then once we instantiate our transformer here, we can call the method fit transform. over the training data to transform or to make a transformation on the training data. So transform, then call the method fit transform, and as an input we have to supply the training data frame. So now the transformation is done. The qualitative variable, which is chas, is already numerically coded, and all the other quantity variables are normalized into a value between 0 and 1. So if we consider the shape of the transformer data, it is 404 observations and 13 input features for the training data. Then once we transform the training data, next we need to transform that of the test data. So in the test data, here for those quantity variables, that's of some of the quantities used to normalize are saved in the transform function here. So for min-max scalar, for example, we use the minimum and the maximum value of each quantity variable. So the minimum and the maximum value of each quantity variable from the training set are saved in this transformer. Then these quantities saved in this transformer are going to be applied for making a transformation over the test data. So here we are going to use what we call the transform method. So in the training sets, we call the method fit transform, but in the test we need to call transform. So now the transformation on the test data is done. So this transformation for those quantity variables is done based on the minimum and the maximum values of those quantity variables from the training data. So here we can determine the number of observations of the transformer test data. Min dot shape, let's say shape. So in the test data there are 102 observations and still there are 13 input features. We can also just convert the data type of that's of the outcome variable. This is not actually transformation. For example, the original that's of output feature of the training data is a pandas series that that's of data type. So if I convert this, now this becomes a numpy array. This is numpy array, this is pandas series format. So this is actually is not a transformation. Just here we are converting the data type polygons of the data format. So this is not a transformation, just a way of converting the data type or the data format. Now transformation is done in the input features of the training and testing sets. So now we can train our model of interest, which is particularly a multi-layer perceptron for a regression problem. So first we have to instantiate our model of interest using MLP regressor. Then once we instantiate, we can fit our model of interest by supplying the training data and calling the method fit. After fitting, we can make a prediction using the method predict and supplying the input features. And for getting the score by default, which is that of the R square measure of performance, we can get the score or the R square value by supplying the input and output features. And we can also get the intercepts or the biases of the neural network by calling the attribute intercepts underscore, and we can get the weights associated with that of the different layers by calling this attribute cofs. So let's go to the documentation of the MELP regressor. So MELP regressor, the first parameter is that of loss function. By default it is squared error, or which is we call mean squared error. And then it says hidden layer sizes equals here 100. Now by default 100 neurons are assumed for the hidden layer. So here we have one number, just one number, that is 100. This one number indicates there is one hidden layer, and that hidden layer consists of 100 nodes. And the activation function, or the nonlinear transformation that is going to be applied on the hidden layer, is ReLU, or what we call rectified linear unit. And the solver is by default Adam, which is just an improved version of what we call stochastic gradient descent. So stochastic gradient descent may stack in a certain local minima in case if the loss function is not convex. So this Adam is an improved version of that of the stochastic gradient descent. And alpha, which is set as 0.001, this is the learning rate. And here we have batch size, that is the number of observations to be considered for updating that of the gradient. So by default says auto, the batch size batch, where is its batch size? Okay, here it is. So by default it is auto. So it will take a batch, or let's say a minimum of 200 observations or number of samples. So as long as the number of observations are greater than that of 200, the batch size is going to be set as 200. So that means 200 observations are going to be taken at a time in order to compute that of the gradient. So these are the parameters. There are also other parameters that needs to be specified. You can look at this documentation. So from a scikit-learn neural network, we need to import this MELP regressor. Now this MELP regressor is MELP regressor class is imported. So we can instantiate the model as MELP regressor. That is just MELP regressor. This is just an instantiation. This is instantiated. So parameters, loss, it is a squared error. Hidden layer sizes. Here we have one value, that is one hidden layer. This hidden layer has 100 nodes. The activation by default, it is ReLU, the solver, Adam, the learning rate 0.001, batch size, that's auto, and so on. So this is an instantiation. Now this multi-layer perceptron or neural network is going to start updating the parameters by initializing with a certain random values. So every time the weights and the intercept are going to be initialized to a certain value. So for ease of reproducibility, we can set this random state to 400, that's of 42, or to a certain number. So let this MELP regressor be assigned to the object name MELP reg. So this is again just an instantiation. There is nothing that we have done here. We just instantiated our container where the neural network model is going to be saved. So if I point to here, it says not fitted. If I click here, you can look at that of the documentation, the one that we saw before, this documentation. So once we instantiate our neural network model, now this neural network model has by default one hidden layer with 100 nodes. So let's fit the model. We can call the method fit and supply the training data. Training input features, which is the transformed one, or the preprocessed one, and that's of the target feature data. So we can run this cell. Now the training is fitted, but the maximum iterations 200 reached, and the optimization has not converged yet, it says. So by default, the maximum number of iterations is set as 200, maximum iter 200. Again here, the same, maximum iteration 200. So we need to increase the maximum iteration to a certain number. Let's increase to 1000. So we have to instantiate first to increase that of the maximum iterations. So random state 42, maximum iter, let it be 1000. And then we have to call the method fit and supply the training data. Then running this cell now, our neural network model is trained and it is converged because there is no warning error reported here like this one. So the number of iterations, it is 1000, right? We have a single hidden layer with 100 nodes. So let's see the performance of the model. We just need to call the method score and supply the training data. So this one provides that of the training R square because we are supplying that of the training data. So the performance of the deep neural network with a single hidden layer consisting of 100 nodes becomes 72.68%. For the test data, again we need to call the method score and pass the testing data. So this is nothing but 63.73. So on the training data, the performance is around 73%. On the test data, it is around 64%. So here we have just a single hidden layer model, and we call it simply deep neural network, or what we call the method of learning as deep learning, because we have one or more hidden layers in between the input and the output layers. And we can also look at the biases and weights of that software neural network model. But for ease of observation, let's reduce the number of nodes to be to 4, and let's just see the parameter estimates. And instead of the default hidden nodes 100, let's specify as 4, and let the maximum iteration be this 10,000, and the random state should let it be 42. And then let's train the model, and let's get the training and testing R square. So with 4 nodes, the training performance is around 70%, which is lower than that of the one with 100 nodes, and the testing performance has also the training performance decreases, but the testing performance increases. It is 67, which was 64 when we use 100 nodes. So now you have four here we have 4 hidden nodes, right? Let me go to the first part of this notebook. So here means 1, 2, 3, we have another node. And we have input features. So each input node is connected with each of the node in the output. Similarly, each of the nodes in the hidden layer are connected with that of the output nodes, and particularly this single output node. So for example, 1, 2, 3, 4, here are 4 nodes. So for connecting that of the hidden layer with the output layer, we are going to have four weights. The weight for the first node, the second node, the third node, and the fourth node. And we have also another bias term here. So for connecting the hidden layer and the output layer, we have also one bias. One bias. And here in the input, we have 13 inputs. These 13 inputs are connected with the four nodes of the hidden layer. So we could have 13 times 4 weights. And here we have also a bias term consisting of an input of 1. This bias will be connected with all of these 4 nodes. So here we will have 4 biases. 4 biases. And the weights are here 13 times 4. So yeah, so here we have a single hidden layer with 4 nodes, right? In the input layer, we have what called the input nodes. Here we have 13 input nodes. So we'll have 13 times 4 weights. We'll have 52 weights between that of the input layer and hidden layer. And for the hidden layer and the output layer, we have 4 nodes times in the output layer, we have 1 node for weights. And regarding the bias, in the input layer, we have 1 bias. And in the hidden layer, we have 4 nodes, so times 4. So we'll have 4 biases between that of the input layer and the hidden layer. And similarly, in the hidden layer, we have 4 nodes. Uh, 4 nodes, and we have just in the output layer we have 1 node. That's 4 times 1. In terms of bias, in the hidden layer we have 1 bias times we have 1 output node. So there will be 52 weights in the what you call in the between the inputs and the hidden layer, and there will be 4 weights between that of the hidden layer and the output layer, and there will be 4 biases between the hidden layer and that of the input layer, and there will be 1 bias between the hidden layer and output layer. So let's see that of the intercepts first. So over our trained model, here this model, we need to call the attributes dot intercepts. So here we have 1, 2, 3, 4. This 4. There are 4 biases or intercepts between the input layer and the hidden layer. And there is 1 bias between the hidden layer and that of the output layer, this one. Similarly, for the estimated weights, we have to call the method cof. So here we have these weight parameters. This should be 52. 52 weight parameters here. These 52 weight parameters between the input layer and the hidden layer. And between the hidden layer and the output layer, we need to have 4 weight parameters. 4. Here we have 1, 2, 3, 4. So here we have so many weight parameters and intercepts that are not actually interpretable like that of the linear models. So now let's see changing the number of hidden nodes, and let's see the impact on the performance of the model. So here we set as it's the number of hidden nodes as 4. Let's increase to, let's say, 64. Again, this hidden layer size specifies only one number. That means still we have one hidden layer, and this hidden layer has 64 nodes or neurons. Let the number of iteration be 1000 and the random state let it be 42. And let's fit our model and get the training and testing scores. So here when we increase the number of nodes or neurons, the training performance becomes around 67% and the testing around 59%. Let us increase the number of nodes from 64 to 128. Now when we increase the performance of the number of nodes from 64 to 128, the training performance becomes 73% and the testing 63. So here increasing the nodes increases lots of the performance of both the training and testing sets. Let's increase further this number of nodes to 256. Now it's the training performance almost remains the same and the testing performance has a little bit increment. And let's increase further to 512. Now both the training and testing performances made an improvement. Let's increase further to 1024. 75, this almost is the same, 69. So yeah. So here when we increase the number of nodes, the performance almost are just having some improvement. Now let's increase the number of hidden layers instead of the number of hidden nodes. So let's consider, suppose the neural network has two hidden layers. Hidden layer 1 has 128 nodes and hidden layer 2 let it consists of 64 nodes. So here we have a two-layer neural network model, not a layer, a two hidden layer neural network model, two hidden layer neural network model. So let me run it. So it is 78 and 71. So previously we have been working on a single hidden layer neural network model. Let's say for example the performance as 76 and 69. Now when we increase the number of hidden layers to 2, the performance in both the training and testing sets have an improvement, 78 and 71. Let's increase the nodes from 128 and 64 to 256 and 128. Again here we have two hidden layers. Okay, here it becomes 84, yeah, 78. So when we increase this number of nodes, there is an increment in the performance of the model in both the training and testing sets. Let's increase further this number of nodes to 512 and 256. Okay, now when we increase the number of nodes to 512 and 256, the training performance has shown some decrement and the testing performance has also shown a decrement. So here we have two hidden layers. So we can increase also to the model to a three hidden layer neural network model. 1, 2, 3. The first hidden layer has 256 nodes, the second 128, and the third 64. Now it becomes 81 and 75. So the testing performance have some improvement, but the training performance is almost the same. Let's change the number of nodes to this and see the performance change. 83 and 78. Now it shows some improvement compared to the previous one. Let's change again to this number of nodes. Okay, it becomes 80 and 73. Now the performance when these nodes are increasing further in both the training and testing sets have shown some decrement. So now let's consider that of the comparison of the usual OLS regression and that of this multi-layer perceptron model. So by default here in the model MLP regressor, if I instantiate here and look at here the parameters, the activation function to be applied in the hidden layer is ReLU. So by default, so far we have been applying a ReLU activation function on these hidden layers. But now let the model be a two hidden layer model consisting of, let's say, 64 nodes and 32 nodes, and let's change the activation function to identity instead of ReLU, which was the default. Instead of ReLU, let's change the activation function to identity, and let's change the solver to LBFGS for a deterministic solver, and let's instantiate, let's specify the random state to a certain number. Now here if we look at the parameters, now here we set the activation to be identity. The number of hidden layer sizes, here we have two hidden layers, 64 nodes and 32 nodes. So this is a deep neural network architecture consisting of two hidden layers, but we set the activation function to be identity. Then when the activation function is identity, that means no transformation is going to be applied on these hidden layers. So let's fit our model for this instantiated model. Just calling the method fit and supply the training data. And let's get the performance scores. 75 and 67%. Now let's instead fit that of the traditional machine learning model, which is linear regression. From a scalar linear model, we need to import linear regression. Then we have to instantiate our model and fit the data and get the performance scores. 75.0, something like that, 68, something like that. There could be some slight difference on the last values of the decimals, otherwise both the training and testing performance are almost the same. So this is the standard linear regression model, and this one is actually a deep neural network model for a regression problem. And specifically, this deep neural network consists of two hidden layers. But since we set the activation identity, no transformation is done on the hidden layers. So if no transformation is done on the hidden layers, the deep neural network architecture and the standard regression model are both the same. So here the performance are exactly the same. But the power of these deep neural network models comes through that of the transformation that's going to be applied on the hidden layers. So the activation function should be something different from identity, either logistic, ReLU, hyperbolic tangent, or any other available activation function. So there are several hyperparameters for constructing a deep neural network model. The first one is the number of hidden layers. There could be 1, 2, 3, and so on hidden layers. So if the number of hidden layers increases, that means the network becomes deeper. Then that is why it is called deep neural network. Even if it has one hidden layer, it is a deep neural network. But when the neural network has, let's say, 3 or more hidden layers, it becomes more deeper. So number of hidden layers is one parameter that we need to find the optimal value. And another is number of hidden nodes at each layer. Usually it is specified as a power of 2. So here, if the number of hidden nodes at a particular layer is large, that means the network becomes more wider. So a hidden layer with 10 nodes is more wider than a hidden layer with 4 nodes. Or a hidden layer with 100 nodes is more wider than a hidden layer with, let's say, 64 nodes, and so on. So the increase in the number of hidden layers refers to how much the network is deeper, and the increase in the number of hidden nodes at each layer determines how much that layer is wider. And in terms of activation function, we have identity. So if we set it identity, that means even if the deep neural network has many hidden layers, it doesn't matter. It is the same with that of the standard linear regression model. We can have the logistic activation function, or which is usually called sigmoid activation function, tan H, or hyperbolic tangent activation function, and ReLU, or what you call rectified linear unit activation function. And in terms of optimizers, we could have a stochastic gradient descent and that's of Adam optimizer. And the number of iterations, usually it is called epochs, can also be considered as another hyperparameter. So we have to specify the number of hidden layers, number of hidden nodes at each layer, and the activation function, the optimizer, and also that's of the number of iterations or epochs. So to determine the optimal values, we can consider what we call that's of the method of tuning hyperparameters using grid search algorithm. So a grid search algorithm is nothing but it fits one model for each possible combination of the hyperparameters and then selects the model or that's of the combination that results the higher or the better performance. So we need to instantiate this grid search CV, and then like that of training the neural network model and all other machine learning models, we need to call the method fit and supply the training data. And to get the score, we can call the method score and supply again the training data for getting the training score, and the testing data for getting the testing score. And the CV underscore results underscore displays a certain dictionary of results of the research CV model. And best underscore params underscore displays the optimal values of each hyperparameter specified. And best underscore provides that's of the R-square performance using that's of those optimal hyperparameters. So to use the grid search CV, first we have to instantiate our model of interest. So here our model of interest is MLP regressor. So let's instantiate it. Now here we are not training the model, or it's not trained yet, but we instantiate our model of interest. This is our model of interest. And let's specify the hyperparameter values. The first, let's specify hidden layer sizes. Hidden layer sizes. here the spelling, everything here should be the same. In naming here, hidden layer sizes. And another hyperparameter, you have activation. So again, you have activation. And for the solver, here you have solver, and maximum iteration. So these values are going to be supplied in a dictionary format. So for the hyper parameter values, for example, for the hidden layers, let's specify this one. Now this means there is no value, therefore this one represents the usual or the standard linear regression model. And let's consider this one. Now here you have one number, therefore this model will have one hidden layer with 128 nodes. And this one again another single hidden layer model with 512 nodes. And here we have two hidden layers, one with 256 nodes and the second with 64 nodes. And let's consider here, this is a 3 hidden layer neural network model with 512 nodes, 128 nodes, and 64 nodes. And let's consider the activation just ReLU. If we are interested, we can add another one. Let's say here, let me add logistic. Let me add another TAN-H. So here we have in terms of activation, we have 3 options. For the solver, let's say CGD and ADAM. And for maximum iteration, let it be one value, which is just 10,000. So in the first, we have 1, 2, 3, 4, 5. In the second, we have 3. 5 times 3, 15. Here we have 2. 15 times 2, 30. 30 times, here we have 1. 30 times 1, 30. Therefore, there are 30 different possible combinations. So for each possible combination, one model is going to be fitted. Then the one having a better performance is going to be selected using this grid search CV algorithm. So these are the hyperparameter specifications which will result 30 different models. So we need to instantiate the grid search CV, and first we have to import this grid search CV class from a scalar model selection. Now this is imported. So in the grid search CV, to instantiate the model, here we need to say grid search models. The estimator is our model of interest MLP regressor. The parameter grid values, the parameter values here specified. Number of cross validations, let it be 5. And return train score, just is to obtain the training performance. By default, it displays only the test performances. So if we are interested to get also the training performances, we can set this return train score to be true. So let me run it. Now this is an instantiation. If I point here, it says not fitted. So this is the MLP regressor, our model of interest. These are the specifications that are going to be replaced based on the hyperparameters here. Estimator, MLP regressor, the parameter grid, this the activation functions, hidden layer sizes, solver, maximum iteration, and so on. Number of cross validations, it is 5. The training performance are going to be also supplied. So now to start training this grid search CV models, we need to call the method fit and supply the training data. So it may take some time. Let me run it. Now fitting the grid search models is completed, but for some of the models, the maximum iteration 10,000 has reached and the optimization has not converged. So there may be a need to increase this maximum iteration. But for now, just let's proceed as it is. So here, so if we point to here, it's fitted. So the research model fitting completed. So the parameters that we specified before are here. We have activation, hidden layer sizes, maximum iteration, solver, and so on. So the best of this is the one with the activation function of tan h, a hidden layer size of 128. That means with just one hidden layer, and that's of 128 nodes. And the solver, the one with SGD, is the better one. So of the different 30 models that are specified in the parameter values here, 2, 3, 4, 5 times 2, 15 times 3, 15 times 2, 30 times 1, 30. Of these 330 possible hyperparameter values, or of these 30 different models, the one with a tiny activation, a single hidden layer with 128 nodes, and an SGD solver is having the better performance. So from this research CV model, we can get the some summary results of all the models using this CV underscore results underscore. But this is actually a dictionary, so it's not that much easy to observe. It is better to convert into a pandas data frame format. So let me run it. This is the data frame consisting of the results for all the possible models, which is actually 30. We have 30 rows, that means 30 models. So each row corresponds to some summary statistics related to each possible model. That corresponds to each hyperparameter combination. Again, still here you have so many columns, so it's not easy to observe or to identify which hyperparameter is better. So instead of looking all the results, it's better to concentrate on the hidden layer sizes, the parameter activation, solver, the maximum iteration, training score, test score, and the rank. So from this table, let's extract only these columns so that it is easier to observe which model perform better. So here we have 30 different models. Here it starts from 0, so it ends at 29. So we have 30 different models. That means 30 different possible hyperparameter combinations. So of this, the one that is having a better performance is this one. A single hidden layer with 128 nodes, a tan H activation function, a stochastic gradient descent optimizer, and these 10,000 iterations. Actually, as we have seen before, some of the models are not converged with this iteration, so there may be a need to increase these iterations. So let's say 15,000, 20,000, and so on. So for now, this is the best one with a single hidden layer with 128 nodes, tan H activation function, stochastic gradient descent optimizer, which has a performance of 87% in the test set and 93% in the training set. So the model with, not this one, the model with, since I changed before, the model with 128 hidden layer, tan H optimizer, tan H activation function, and Adam optimizer performed better compared to all the other models. So we can directly extract the optimal values of the hyperparameters using these best params. Just we need to call on our research models object using this attribute best params underscore. So the activation is tonnage, hidden layer size 128, maximum iteration 10,000, and the solver stochastic gradient descent. And how much is the score? We can get using this best underscore attribute. It is 87.17%. So the number of cross validations is 5, therefore this is the average performance across the 5 folds. So we can directly also get that's of the performance using the training data. This one score supply training data. This is the performance on the training data. But this one is actually the performance or the average performance across the 5 different cross validation folds or cross validations. Similarly, for the test score, using the optimal hyperparameter values, for our test split, the performance is around 71%. So for the training, it is around 78%. So we call this score method over our research models that we have defined as a means of searching the optimal values. Here, this one. So these are just the best values of the hyperparameters. So we can train a new model with these specifications: setting activation tonnage, hidden layer size 128, maximum iteration 10,000, and solver SGD. And as I said before, this should be increased because this model may be one of the ones that didn't converge with these iterations. So the final model should be trained with the optimal hyperparameters. So the hidden layer sizes for our case is 128. So I have to change this to 128 instead of the activation value. Here it is tan h. So I have to say tan h. Solver it is SGD because here SGD is better. So iteration let it be 10,000 and let's see. In case if it is not converged, we have to increase this value. So we have to train the model and then get the performance scores. So 78, yeah, it's converged. So 10,000 is enough for our model. So the performance on the training set is 78%, and on the test it is about 71%. Therefore, this model is the best model of the different candidate models, which has a single hidden layer with 128 nodes, it has an H activation function, an SGD solver, and 10,000 iterations. So here let's check in the research CV using our training data. It is around 77.6, it is 78. In the test it is 70 for the final model, but it says 70.5, yeah. So there are slight differences when you obtain the score using the training data and the testing data, and the one that we train our model using the optimal hyperparameter values. So this slight difference may be due to here the random state we specify as 42, but we don't know what random state is used in the research models. So that's why this value and this value have some slight differences, and this one has some slight difference. Otherwise, this one is based on the optimal hyperparameter values, and this is again based on the optimal hyperparameter values that are defined in the research models. So this is all about today's video. In the next video, we'll consider how to implement this deep neural network algorithms for solving classification problems. Thank you.